So up to this point, we've only talked about higher order, first derivatives, meaning the just the normal derivative of a function. So the rate of change of whatever quantity that function is dealing with. So for example, if we have a function which defines position, which we usually call s of t. So just for example, let's say that we have negative 16 t squared plus 10. Okay. Or maybe let's make it a little bit more interesting here. Let's make it negative 16 t squared plus, say, 12t plus 10. Okay. So let's say that this gives the position at time t. So usually we say t is in seconds, position in this case might be in feet. Okay. So just for example, at time 0, right, this is 10 at 10 feet. Okay. So it's starting at maybe like a height of 10 feet, since this is going to be an upside down parabola. Then when we look at the derivative of this, this would be the rate of change of the position. So how much is the position changing? How quickly is the position changing, right? So we call this the velocity. Okay, and the velocity, the derivative is negative 32t plus 12. Okay, so this is the rate of change in position. Okay, in other words, it's like the slope of position. So we describe this as a ratio of feet to seconds, right? So again, for example, at time 0, the initial velocity would be 12 feet per second, right? So it's initially, so if you imagine this being like a ball thrown out of a window, for example, the window is 10 feet high and the initial velocity is 12 feet per second. Okay. So now we can take this a step further, right? So we don't just have to look at what we call the first derivative, which is the rate of change in the position. What if we want to know how quickly is the velocity changing? Because the velocity is not a constant function, right? The velocity itself is going to be different at different periods of time. So for example, after 1 second, the velocity is going to be negative 32 plus 12 equals negative 20, right? Negative 20 feet per second. And this is quite different because velocity is telling us the direction. It's telling us that initially, if we're throwing a ball out of a window, so I have the graph for this pulled up, but let me just draw it for a second here. So this is 10. So let's say we're throwing it out of this window. The velocity being positive means that the position, the change in the position is positive, meaning that it's going upwards. But if the velocity is negative, that means that the position is decreasing, which means that this is going downwards. So this is giving us a lot of information here, how the velocity is changing. So can we look then at the rate of change of the velocity, meaning the rate of change in position, right? So in this context, we would call this acceleration. Okay, so this is s prime of t, first of all. So s, we would say double prime of t, is the second derivative of the position function, which is the first derivative of the velocity function. And these are all with respect to t, by the way. It's going to be negative 32, just a constant. Again, we call this acceleration, so we might call this a of t, for example. Okay, so negative 32. So if you look at a lot of these horizontal motion problems, where you're kind of like imagining this upside down parabola where you throw something out a window, you're often going to see this negative 16 in here. And that's not on accident. That's specifically because when you do the acceleration, you get negative 32. And that is the acceleration due to gravity. Okay. So specifically, this is negative feet per second. This is the velocity, and we're looking at how fast this is changing per second. So it's feet per second per second. So we often write this as negative feet per second squared. Okay. So we'd say negative 32 feet per second, or negative 32 feet per second squared. Okay. So this is the acceleration due to gravity in feet. In meters, I believe it's negative 4.9. Okay. But because the acceleration is going down, this tells us that the velocity is decreasing. Okay. Which means that, so it starts at 12 and then it goes to 0. The velocity becomes 0 at the apex of the position here, right? And then it's going to keep, the velocity is going to keep decreasing. And it's going to keep going down by the same amount, right? At the same rate. But it is going to constantly go down. And it's always going to be going, so it's just going to keep getting more and more negative, basically. Of course, in a real world context, this is just going to hit the ground and then it's going to stop. But if there was no ground there, if it could just keep falling, it's going to keep, its velocity is going to keep increasing, right, downwards. And of course, we're not taking into account air resistance and things like that in this context. But the point is that we can look at another derivative. We can look at the derivative of the derivative, right? And you don't have to stop there. In this context, maybe we do, because now if we look at the derivative of acceleration, we're going to get 0 because it's a constant function, right? So then any derivative after that's going to be 0. But in other situations, you don't have to do that. So I did pull up the graph on Desmos, so we can just look at that real quick. A better drawing of this, right? So again, this is the initial function. So it's like we start at 10, and then you can imagine like you throw the ball upwards at an initial velocity of 12 feet per second, which you can see on the graph right here, and the blue line. And then as it's going upwards, the velocity is going down really fast, which makes sense because it's being pushed down by gravity, right? That acceleration due to gravity. So the velocity is decreasing until you hit the apex. When you hit the apex, that's going to correspond to where the velocity is 0. Okay. And then your position, now that you're at the point where your velocity is negative, now your position starts decreasing, right? So it's going down and down and down. Eventually it will hit 0. So that's at 1.25. So like we could find what the velocity is the moment it hits the ground. It probably will be too far on this graph to really see. Let's see. 1.25. Okay, we can see it's about negative 28-ish feet per second. And then we also can look at the acceleration. The acceleration is this green line. So that's the slope of the blue line, the velocity. And it's just a constant function at negative 32. Okay. Okay, so this is also helpful when we're going the other way. When we start looking at the antiderivatives, you can start with the acceleration and then you can build up to the position function. So in general, you can just keep taking derivatives of a function. Eventually they might just be 0. Or, you might, even if just because you can take the first derivative, like if a function is differentiable once, it doesn't necessarily imply that it's differentiable a second time. So even if the first derivative exists, the second one might not exist. But in general, for nice continuous functions, you can just keep taking the derivative. I say nice continuous functions because continuous functions isn't enough. Right? We've seen in the absolute value function, for example, which is continuous, you can't take the first derivative at every point. So let's go ahead and just look at some of the notation for this first. Okay, so I just showed the double prime there. But of course you don't want to just keep tacking on primes if you keep taking derivatives. So in general, we have f of x, f prime of x, f double prime of x, and then at 3, sometimes they add another prime, sometimes they'll switch over to the other notation, because at this point it starts getting a little messy. But if you want a higher order derivative, you put a 4 in parentheses here. Okay, so that's in the parentheses is to distinguish it from a power. Okay, so sometimes they might do that for 3. But just in general, you can then do fn of x, right? And that would represent the nth derivative of f if it exists. Using the Leibniz notation, you have your dy dx. The notation for the second derivative looks like this. So remember, the y here is saying what you're taking the derivative of, so it doesn't get the squared part, because sometimes the y is written down here, for example. So it's written like this though, so d squared y over dx squared. So it's saying take the derivative with respect to x twice, right? And then you could do it 3 times, and then you could just keep doing that n times. So again, a lot of times when we're taking the derivative of things like polynomials, eventually they'll just all be 0 at a certain point, right? Once you reach whatever the derivative is corresponding to their power. So like if we have x cubed, the derivative would be 3x squared. The second derivative would be 6x. The third derivative would be 6. And then the fourth derivative would be 0, right? So this is f prime, f double prime, f triple prime, f quadruple prime, you could say. But some functions you could just take the derivative of forever, right? Like e to the x, the derivative is e to the x, and then the second derivative is e to the x, and the third derivative is e to the x, right? So that's never going to end. Other things like sine, for example, the derivative is cosine, and then the derivative of that is negative sine. So the derivative of that would be negative cosine, right? And then we're back at sine, etc. So it's cyclic, just like the the sine function itself is. So sometimes you can do this infinitely, sometimes you can just do it a few times. Even if it eventually zeroes out, like if the derivatives are all 0, we still say that it would be infinitely differentiable. So this concept will be important at the very end of this class when we look at Taylor series. Taylor series are where we can basically approximate pretty much every function with a polynomial written as a infinite series. But one of the conditions for being able to do that is the function needs to be infinitely differentiable. So you would just basically need to show that it would, you would just take a few derivatives and show that it's following a pattern that shows that it would be infinitely differentiable. So a good example of where something like this might fail, where it won't be infinitely differentiable, but it is somewhat differentiable, meaning that at least the first derivative exists. We could consider something like the absolute value of x times x. Okay. So looking at the piecewise definition of this, the absolute value of x is equal to x if x is greater than or equal to 0. So for multiplying by x, this is going to be x squared if x is greater than or equal to 0. And likewise, it's going to be negative x squared if x is less than 0. Okay. So you should be able to easily show that this is continuous at 0. Though again, it doesn't matter for differentiability purposes, right? Because continuity doesn't give you differentiability. But we can take the first derivative of this. Unlike the absolute value function itself, which is sharp at 0, this one actually looks more like this. It kind of looks like a cubic function almost, but the values are different, but it has that same general shape. So the first derivative does exist. The first derivative is actually 2 absolute value of x. Okay, you can actually show this from the product rule. F prime of x equals the derivative of the absolute value of x is the absolute value of x over x, and then times the second one, plus the absolute value of x times the derivative of x, which is 1. So these cancel, and we're left with 2 root x. There's a little bit more you'd have to do here because the absolute value of x is not actually differentiable at 0. So you're kind of ignoring that point of 0 here. But this is the general gist of it. But now, so the first derivative does exist. It is differentiable once, but now you can't take the second derivative, at least at 0, because this function is not differentiable at 0. Right, we've already seen that the absolute value of x is not differentiable at 0, and so 2 times the absolute value of x is that's not gonna change anything. It's still not going to be differentiable at 0. Okay, so things can be once differentiable, but not twice differentiable. So just being able to differentiate it once doesn't necessarily imply you can infinitely differentiate it. But anyway, so yeah, so we're more concerned. Usually we're concerned, I would say one of the biggest applications of this is in things like with velocity, because the derivative of velocity is acceleration. So that gives us a nice physical interpretation of this.